I'll try to introduce what is CFD. Please switch off your microphone because it's
भी ज्वाइन कर रहा हूँ यार इसमें।
unnecessarily create a noise. So the way we will go about it is sometimes people call it means the abbreviation computational fluid dynamics, but in jokingly sometimes people call it as a colorful fluid dynamics. So basically we reproduce the results in colored map, etc. So that's why people jokingly said it's colorful fluid dynamics, but eventually uh, the full name of the CFD is computational fluid dynamics. As it's a FDP or faculty development program, so I thought that I'll decide on the learning objective of the session, that is familiarization with the computational fluid dynamics. Like who doesn't know at nothing except the fluid dynamics, for them it will be a familiarization. We are not going to go to the nitty-gritties of the schemes or the methods, etc. So you will come to know some jargons, some what is this, what are the applications areas, what are the special features of it, etc. from this class. So the learning objective for this session will be the familiarization of computational fluid dynamics. So how will we go about it? We first see please mute your microphone. Some of you are not, I am listening some sounds and it's creating some problem. So what, why and where to of CFD. Okay. And then we'll discuss that how it comes. If we don't know the modeling part of it, then we can't apply the CFD. So then we'll see that what it is, like if we know the equations either in the partial differential equation, or if we see the integral form of the equation, then what are the numerical methods? Because you know the computer doesn't understand an integration sign. Okay, some software if you write integral, but that will evaluate, but internally computer doesn't, the chips level computer doesn't understand, it only understand the matrix level, you know. So you have to give the computer in a such a way that we are all using some softwares that basically having a interface which translate all these things in the what computer does understands. So when the CFD was developed, that time, if you see the genesis of it, basically we have to give the partial differential equation in a transform that to a algebraic form of equation, where we can understand the matrix at least. Okay. Then we will see the CFD processes. An example of these CFD processes. This is the basically a short way about that how we'll go about this presentation. Now, what is this CFD? Already I told it's a computational fluid dynamics. Historically, analytical fluid dynamics, like you see the some solutions like pipe flow or something like that from the Navier-Stokes equation. These are called analytical, or a vertical flat plate where you find the Blasius solution. So, or a horizontal flat plate where you find the Blasius solution. So these are called the analytical fluid dynamics. And then you can do an experiment also, that is the experimental fluid dynamics. But the CFD, the computational fluid dynamics, was only possible when you have a high-speed digital computers. Earlier, with the invent of the computational power, we are going very easily. Like earlier, a simple equation, it was taking a 4 days, 5 days time. Now, very complicated coupled equations are also in a couple of minutes it solves. So it's all invent with the computational power, whatever we have seen in the last 20, 30 years. Not able to see the presentation. So okay, I'll go in this mode. I think you can see it now, Anikita.
Sir,
Okay,
yes, it is visual. It is visual.
okay. So computer simulate, it's all depends on that computer power or computer basically computational power, whatever has been evolved in the last 30 years. Now our desktop computers can do it in a 20 minutes some flow simulation, which involves the complicated fluid physics. Now, the objective of the CFD is to model a continuum fluid, because CFD as such works with continuum mechanics assumption, like continuity equation we very much use. Like if it is a ratified assumption, like when we see that basically the stratosphere has only 2% of the atmosphere, so it's highly ratified. So those cases, the traditional CFD will not work, whatever we understand as the normal CFD. So it basically it's a continuum mechanics or continuum extension of the continuum mechanics, where continuity equation or the mass balance equation is very much valid. And we generally transform the partial differential equation, which is the acronym of the partial differential equation, that is PDEs, and discretize these PDEs into algebraic equation. You can, I'll explain that in the later part of the session, that how to discretize the PDEs in terms of your algebraic equation, and then that algebraic equation you can solve, and that will give you different scalar variables, vector variables like velocity, pressure, temperature, etc. So this is the objective of the CFD. CFD as such is a partial differential equation solver, and however you are transforming the partial differential equation in terms of algebraic form, and then the algebraic form, you know, that computer can solve in different ways, that you will see it in today's lecture. Some snips also you will get, and in the consecutive lectures during the course you will also get familiarized with it. Now, why we use CFD? In analysis and design, the simulation based design, instead of build and test, like you have to do lot of testing, lot of making and prototype. So instead of that, if you do CFD, it's much cheaper option when you have a computational power with you. Now, sometimes what happens that it's a full scale study, like airplane, a full car. It's not possible to do the experiment in a airplane, or very not easy to do that, or a full scale ships. Then you have some hazardous material like radiation, nuclear reactor, pollutions. So those cases we use CFD, and as well as we want to understand the inner meaning of the flow physics, and explore the flow physics, weather prediction, or maybe a simple fully developed flow. Simple in a pipe channel, a fully developed flow, we want to understand what is the pressure variation, what it really varies after the some length or not. So those things, the nitty-gritties of it, you can easily play with it in a, if you know the model or if you know the correct equation, then you can solve it. And that is the basic reason that why we use the CFD. Now, where we should use? You name it, we can use it. That is my answer. You name it, if it follows the continuum mechanics. Otherwise, other form of CFD like can be used. But you name it, like starting from aerospace, appliances, automotive, biomedical, chemical processing, HVAC, hydraulics, marine, oil and gas, power generation, sports techniques or sports gadgets, everywhere you can use. Now you see this how we'll see that when my flight is going to bombard the right kind of bombs, or pressure variation along the wing of a aircraft, or you see the hypersonic launch vehicle, this there the radiation is going to take a pressure distribution you want to see. Like the aerospace has lots of applications. Okay. Now the appliances, I'll tell you the refrigerators where the cooling flow will be given or where the cooling flow will not be given. These are all generally, as a matter of fact, that when we discuss the machinery application, a simple ceiling fan, that also people, you have seen the advertisement also that people are doing the CFD study and design the ceiling fan or table fan or things sort. So there are lots of appliances these days. Without CFD you can't move anywhere. So in this slide says that the when we are seeing as the defrosting or no frost mechanism, that where the cooling flow will be in a refrigerator, that otherwise you have to change the different flow rate, different orientation, different so these things you can easily change in a CFD paradigm and test it and find the optimum one. Next slide. The automotive one is the lots of application. Any industry, wherever the flow is there, the automotive one, like is external aerodynamics. You have to reduce the drag here. The undercarriage aerodynamics, where basically you have to require a cooling flow because of the engine and all these things. The interior ventilation of the inside the car or vehicle, the engine cooling, everywhere you will find that the CFD has been done for the first cut design. After the first cut design, the finalized one, before we do the development, we need a CFD for this. Now biomedical, it has a little complicated CFD because means this is basically a centrifugal pump, and where the blood is getting like pumped, and if you want to test it for a several, like it's a non-Newtonian fluid or Newtonian fluid, you have to do this several times of testing and make it proper one, like a low cavitation is occurring or not. All these things can be easily tested with the CFD. The spinal catheter, like when we do a long operation, then during like if you give a very high dose of anesthesia, then eventually patient are going to die. He may not come back, depends on his health. So we do people do anesthesia where you can give a catheter in the spinal cord, and that's the amount of flow of the anesthesia gases. All these things can be determined by the CFD, and then people use the experience of the doctor. The temperature and natural convection inside the eye of a laser heating, when you do a laser surgery in the eye, the LASIK, whatever they does. So the company LASIK, it's basically the laser probes, etc., has been developed based on these. Now, chemical processing, it's a basically multi-phase flow in all the chemical industries, the reactor vessels or a screw extruder or a shear rating distribution in a screw extruder. Everything is mostly the multi-phase flow, and this multi-phase flow can also be, it's very difficult to do an experiment there in a multi-phase flow. So, and you have to change the model, you have to change the prototype several times. So it's better to go for a final design. You do an extensive CFD with the correct model, correct equations, correct approximations, and try to design that. Next one is HVAC. The interior design of the in a room, I'll give you a very pertinent example. Recently, we worked with the how we can suppress the COVID inside a healthcare sector, and we found that if we change the turbulence level and give you a proper flow direction, then may not, because healthcare sectors obviously will have a air conditioning facility or built-in air conditioning facility, otherwise the instruments are not going to work. So in a operational theater, you have to, and there it's circulating, the air will spread the COVID like anything. So if you try to use a redistribution of the turbulence model, or use a ESP, electrostatic precipitator, and that will basically take the agglomerated coronavirus cluster, and it will help. So those things, otherwise you have to do the real life experiment. CFD you can do easily with these aerosols, and how the aerosol dynamics looks like, how you can. So this is a very pertinent example. Otherwise also how to create the flow distribution inside the chamber, inside the ducts, etc. You can easily find out with the CFD. Now hydraulics and marine, it's also like this. Like you can do hydraulics there, like in a pipeline or a bridge. So hydraulics, obviously it's related with the fluid and the flow. It's not very easy. Like bridge, the extension of the bridge, etc. also is required. Now marine, you see that there is a full scale your ship, and that model, if you want to make up and try to in a water tunnel with the dimensional homogeneity, etc., that will not give you the right kind of answer except you do a CFD properly. So you can do a full scale model CFD and try to find out that. Now you see that oil and gas, very one of the major user of the CFD sector, because they are cash rich also, and then they can deploy different type of new technologies. So it basically multi-phase flow. The volume fraction you can see in the oil separator, or a drill bit, whatever you are drilling in the oil rig. So all these things you can easily simulate and give you the accurate dimension and parameters. So today the computer aided engineering CFD is an integral part of it, and you can't help without that. In a power generation sector, all the turbo machines, cooling towers, flow pattern, everything is designed based on CFD. Especially that people like GE and all that, they did this CFD and then designed the final design based on this power generation equipment. In a burner, otherwise the experimentation in a combustion is not very easy, and you have to do the very detailed design simulation. That's why it's required. Now if you taking a cricket ball also, how it is going to be seen, in a sports, in a cricket ball also, if you, how does it in a it seems it rotates, the rugby ball, how it rotates, a different your sports equipment, these are also bat or racket, everything is going to be first the computational fluid dynamics based studies has been done, and then it has been designed. Now the physics, obviously the CFD is a software. If you are using it, that is a black box. There are two types of CFD codes generally we found out. Like if I do a PhD problem, I develop my own code, then I'll do a, basically my problem domain is very narrow and very focused. You know, it should not be a generic one where you will be seeing the all kinds of flow will be able to solve. Like some softwares that solve the turbulence better, some software they solve for the free surface flow better, some software they solve the multi-phase flow better, some software solve the compressible flow better, and there are some very few softwares they solve all the problems in a decent manner. So if you classify the flow like viscous or inviscid, I am assuming that people know the basic flow of fluid mechanics, so I am using the jargons whatever is used in a fluid mechanics class. So viscous or inviscid or turbulent or laminar, incompressible or compressible based on Mach number, single versus multi-phase flow where the capillary forces or surface tension is going to take a dominant role there. Boiling example. Thermal density means natural convection, basically the Prandtl number, the gamma, the Grashof number, the Eckert number, etc. is going to take a major role. Now free surface flow, like when you are injecting a jet, or the surface tension based Froude number and Weber number, then chemical reaction and mass transfer. Now if you see the Fluent, the generic software ANSYS Fluent, they solve all these problem very decently. So but when there is two approach. When we write my own code or do a specific problem, we basically concentrate on that specific problem. We may not, now people are but if you want to develop a software which will say the entire gamut of this problem, then you have to be very specific, very choosy about the schemes. Now, physics, understanding the physics of the problem is very important, because otherwise you will not be able to select the right kind of model. So fluid mechanics is categorized in inviscid and viscous flow. The viscous flow can be categorized based on the Reynolds number, etc., the laminar and turbulence. Then this viscous flow can be this inviscid flow can be incompressible or compressible based on the Mach number. Like mostly it's an incompressible case of water, air, and acoustic problems. It will have a compressible one. So these are all models available in your CFD software. But if you don't know that what is my model, what model have to be selected, then you will be in a real problem. The internal flow like pipe and valve, external flow like airfoil or ship or aircraft. Generally, this traditional CFD software or CFD, what we do is solve the Navier-Stokes equation. Okay, the Navier and Stokes, they give this equation in 1845 or so, and we'll see in a moment. These are the differential form of the governing equation, and this is nothing but based on the Newton's second law, P is equal to mf, and in a control volume in a differential form, and this still is valid. And moreover, these equations are nonlinear, and these equations are coupled. I'll explain what is nonlinear and coupled. So these are the equations, the Navier-Stokes equations in 3D Cartesian axis, and you see the u is the x directional velocity, v is the y directional velocity, omega is the z directional velocity. Then you can express, this is the incompressible fluid flow where only the viscous term is considered, the other body force, etc., is negligible in comparison to that. I think you have a session based on this transport equation, but what I will tell in this class is basically what is the typical behavior of the Navier-Stokes equation. So these terms are called local acceleration. This is the term is called convection. This is the pressure gradients in all the three directions, and this is the viscous term. Okay. And obviously the mass flow rate is a continuum mechanics, so mass conservation equation or continuity equation will be valid. But what is the problem in that? You see that u del x in the first x direction momentum equation, v del y, and omega del w del z. These are the nonlinear terms. Nonlinear term is the coefficient, and the coefficient is the dependent variable. Just whatever differentiation we are going to make, this variable and this coefficient is the same. So then we can call it as a nonlinear term. So we have a nonlinearity in the equation. We have a nonlinearity in the equation. We have a coupled, because if you obviously only u will not give you, right? So number of equation, you see that u unknowns, u, v, and omega, and p, because properties and etc. is known. So there are 3 equations and 4 unknown. There are 3 equations, like u is one unknown, v is another unknown, and omega is another unknown, and p is another unknown in that particular x, y, z in a fluid domain. So you have 4 unknowns, 3 equation. What you will do? You have to introduce a equation. Number of equation, number of variables has to match. Otherwise, it will not be a determinant problem. So that will help that, okay, I have a continuity equation there, but as such, there is no direct pressure equation. We getting a 4 equation, 4 unknowns. So it's a determinant problem, but eventually there is no pressure equation as such. And moreover, these pressures are in a gradient form. So the pressure drop in a particular leg. You don't know the exact pressure there, but you have to find out the pressure. So these are the problems. And that's why such a complicated equations for a generic solution of Navier-Stokes equation still doesn't exist for any domain. And that's why we have to do an approximation. And that's why we need a numerical method for that. Okay? Is that clear to everyone? Is that clear to everyone? That why?
Yes.
Okay.
Yes, sir. Yes, sir.
Okay. So that is the whole lot of problem, that we have a nonlinear equations, we have a coupled equations, and we have pressure equation is not there. Okay, and to do that, the special features already I have discussed, and solution methods, these also I have discussed. Now these solution methods, what I told, that basically we are discretizing we have to discretize this. Discretize means the computer is not going to be able to understand that the differential form of this equation. Okay, so you have to give in such a way that it can be expressed in an algebraic equation. So one of the way, like if you see one of the ways algebraic equation, one of the way to express this algebraic equation is the finite difference method. Okay, in a finite difference method, what we do is we take the governing equation and in a differential form, and that domain on a grid, replacing the partial derivative by approximate terms in terms of the node of the function, one algebraic equation per grid, so linear algebraic equation will be transformed. So if you write the Taylor series expansion, you write any function, right? Here there are derivatives, either first order or second order. So you have to write the first order or second order derivatives in terms of finite difference. Now, finite difference, if you write the Taylor series expansion, etc., like this is the traditional Taylor series expansion, and you can find out the d phi dx, the derivative, the first derivative at the ith point is phi I plus 1 minus phi I by xi plus 1 minus xi. That means the delta x here and the two values. Now these is the forward. Like if you don't, if you know this, if you know the next value of it, the ith direction, these are all one dimensional. And obviously this forward difference is going to be applicable when you know this at phi I plus 1. When you don't know, you know the backward value, you can do a backward difference, phi I minus phi I minus 1. Okay, and if you know that both the values, then it will be phi I plus 1, phi minus phi I minus 1, means it's a 3-point formula basically. You can express that also. So this is a central difference when you know the forward and backward both the values. So this is the way you can find out the derivative in the first order. This is the way you can find out the derivative of the second order. Like if you write basically the del square phi del x square, the d phi dx I minus 1, d phi dx I, and xi plus 1 minus xi. And obviously that it will be expressed in this way, and then equidistant spacing, like equally spaced grids, it will come as a phi I plus 1 minus 2 I phi I minus I plus 1, I minus 1, and delta x square by O. But one thing, when you are using the Taylor series expansion, you are taking a first order approximation. Here when I am writing this expression from here, there's other higher order terms I am neglecting. Okay, other higher order terms when you are neglecting, so obviously there will be some truncation error up to which level. So whenever you are truncating, these terms are going to create an error from the exact solution. Okay, so we have to mention this is a first order accurate or is a second order accurate. Okay, this is the one way of discretization. But in real life, the life is not that easy. Engineering substance, engineering geometry is not that easy. So you will get highly irregular object, highly nonlinear surfaces object. So those aspects, finite difference has some drawbacks. Still people are using, the maths people extensively use the finite difference approach, where there is a simple geometry, simple, but their mathematical rigor is more. But when we have to get a flow across a pump, it is a complicated geometry. Then during that time, the traditional finite difference is not going to work, because irregular surface, irregular geometry, you need a lots of substitution, back substitution, etc. Okay. So what we do is we use another method called finite volume. You can see this is my domain, and by the way, when you select the computational domain, it's very important that how you select the computational domain. Say there is a flat plate and there is a flow over it. Okay, the flat plate, where you will draw the computational domain in y direction, that is very important. Otherwise you may not be able to capture the boundary layer if you are taking a very short height, or if you take a very long height, then ultimately your computational time is going to increase, because number of equations are going to increase. Okay. So in a finite volume, there is an approach like this is not the finite difference. This comes from the integral form of the conservation equation or the momentum equation. Sometimes it's called the integrated over control volume also. So what we do in this case is we consider the node point as a center of the grid, and we integrate over that control volume. Okay. And what is happening here is that you can fill up this is your control volume, say you can fill up with any types of objects because you are integrating over the surface. Okay, and surface and volume basically. So you can fill up this object computational domain with a irregular, regular objects, and that is called structured or if you are unstructured grids, and that eventually helps to deal with the irregular object. So what we do in finite volume is the finite volume is methods uses the integral form of conservation equation, and finite volume defines the control volume based on the while finite difference define the computational node located at the control volume center. As I was talking about, this is a compass notation, so it's a north, west, east, south, and global conservation equations has to be maintained automatically, and this is the conservation equation you can write from different surfaces like x direction, y direction, if it is the z direction, the summation of the control. Based on that, the discrete location, whatever the variables are to be calculated, are defined as a numerical grid. Like earlier in a Taylor series expansion, what we do in a say x direction, some bar is there, you have to find out the temperature difference, etc. So you divide that in 100 points, say. The more number of points, the number of points and number of equation has to be like, when we talk about in CFD, okay, I have taken a 1 lakh grid. 1 lakh grid means that you have 1 lakh simultaneous algebraic equation you are solving, and that's why it's taking so much of time, you know. So the numerical grid is a representation of the geometric domain of the which the problem is to be solved, and it divides the solution domain into finite number of subdomains. And typical numerical grids are structured, block structured, like couple of grids together. Like in a flat plate problem, we can take inside the boundary layer some coarse fine grid because you have to capture the boundary layer, and outside you can take a coarse grid, means the grid spacing is more. Unstructured grids where you can basically apply the different types of geometry in a sponge analogy. Now, as I was telling that the pressure equation is not there, so one of the approach is that eliminate the pressure. Eliminate the pressure, and you see that del P del X, say there is a two-dimensional flow. I will go back to that Navier-Stokes equation. There is a two-dimensional flow. Now, if I differentiate it with respect to y and if I differentiate with respect to x, this equation I am differentiating with respect to y, and this equation I am differentiating with respect to x. Then I do a subtraction. So the pressure terms are going to be cancelled, because both the cases you are going to get a del P del X y and del P del X y, del y. So you will get only the velocity terms and viscous terms. That you can play around, and that is generally people do in most of the two-dimensional flow simulation. That is called stream function or vorticity method. Okay. Now, as I told that there is no pressure equation, so you have to link up with the pressure. You have to additionally add some pressure equation. When you see the CFD software, they will give you some schemes. You want to go for a simple or a simpler or simple C. Okay. So this is one of the scheme called semi-implicit method of pressure linked equation, and this is the algorithm for it. I think you have the special class for these kind of schemes, etc. Don't worry for that. But one thing you have to learn from today's session is that there is no pressure equation as such, and we have to use a pressure equation to solve that pressure inside that whatever the point we are looking for, the velocity, etc. Because we want velocity and pressure in the same point simultaneously, right? So once you have discretized either Taylor series or finite volume method, you are getting a equation A phi equal to Q. So these equations has to be solved. This is, you can just invert. You have to find out the phi A inverse Q, or the peculiarity of this A matrix will be a sparse matrix, highly sparse matrix. You know what is a sparse matrix? Sparse matrix is the most of the elements except couple of diagonal elements are zero. So highly sparse matrix, to invert that is not easy. Normally you can't, normal algorithm for a say 100 of elements are zero, only 2-3 elements you have some non-zero values, and you have to invert that. You may not get the inversion for that. Okay, so sometimes people use a converging, means we use the converge, we assuming like, you know, the Gauss seidel iteration, like there are those kind of thing, like initially guess values and then iterate and then convert some solution for that. Now the matrix, whatever I was telling about, this A matrix is going to be highly sparse, and that there I am marking as a sparse matrix, non-zero elements, and it's not traditional. Like I have seen that you have a class for this tridiagonal matrix algorithm, etc. So I am not going to that nitty-gritties for that. So basically, this is the problem. First problem is you have to solve the coupled nonlinear partial differential equation. Only you have a 3 equation. So you have to basically introduce a 4th equation, which is continuity. Physically that will valid because the law of physics, and you have to do that in a complicated geometry. So the normal Taylor series expansion will may not work. So you have to use a finite volume or finite element kind of techniques. The finite volume is popular in because Fluent and all these things are written in finite volume techniques only. Okay, because it can takes the irregular geometry very easily. Now convergence criteria, very important. Very important concept. When you are taking a convergence, the difference between the two successive iterations, this is, if it is less than some stipulated decided value, then you can say it's converged. This kind of convergence is called absolute convergence. Okay, now if you say that the ratio of it is less than that, then it's called relative convergence. Say I give you one example. When I was studying porous media flow, the velocity is very less, and especially in natural convection, you know that velocity will be anyway the less. The when you are studying in a porous media, the velocity will be much less. Generally, what people do is they use a 10 to the power minus 3 to minus 6 this epsilon, and like use that. So your initial value itself is 10 to the power minus 6. Then if you go for a 10 to the power minus 8, then it will take a long time to converge. It may not converge also. And the thing is that at the first two iteration, you will converge. But that is not the case. You are not going to get the right value because the value itself is 10 to the power minus 6. If you are taking the modulus of a 10 to the power minus 6 level value, it will give you 10 to the power minus 6 only. So it within 2 iteration it will solve. But if you take a relative one, like always select in a CFD software a relative one. There is a safer one, because the relative one, like if it is a 10 to the power minus 6, this is a 10 to the power minus 6, this will come 1. So the relative residual, if it is 10 to the power minus 3 or 4 or 6, then it gives you a real picture or real iteration value. Is that clear? Is that clear? Hello?
Yes, sir.
Okay. Now we are
Yes, sir.
not going.
Yes,
Now
sir.
we are going to.
Yes, sir. It's clear.
Can you? I missed one question. Shiru Sharma or somebody. Can you please post that question? Okay. Now we have to see the CFD process. Assuming we are going to all we are going to use is the CFD software. I already told there are two approaches. You can write your own code. Now, very few people like whoever has. Acha, can you please tell in Hindi? Okay, I can speak Hindi at least. I'll try to give you some. ये जो CFD process है that means that you एकदम पूरा हिंदी में बोलना थोड़ा सा मुश्किल हो जाएगा क्योंकि द टर्मिनोलॉजीज आर इन नॉट इन हिंदी टर्मिनोलॉजी आई डोंट नो okay anyway I'll try to use some of the Hindi words
Actually, sir, most of the participants from South only. So totally Hindi. Actually, few are the North, and most of the participants are from South. So they
okay
can
okay
understand English very well.
okay 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 okay. So the CFD process, there are two approaches already we have discussed that means somebody is doing a PhD or some research problem, they develop a code and then you have say 10, 20 PhD student, different types of problems you have solved and then you can club that code and that's the way Fluent and all these things came up in US. Texas A&M. Okay, so when you are writing the first code, during that time the generic software not in the mind, right? But I am assuming that we are going to use a CFD as a black box, as knowing the basic terminology and basic models or basic physics of the flow, will be able to solve the flow. So first thing is geometry description. What geometry? Say there is a complicated geometry and if you want to totally take the CAD or CAE based drawing, that will drill bit say. Very complicated geometry. So there you have to reduce so that it can understand the capture the flow physics. So you have to be very judiciously create the geometry. Only if you take the drill bit CAD or CAE and put that in your CFD software, it will take unnecessarily lot of time. It's like extrusion process in your chemical engineering. So those things you have to judicially select. I gave you an example of a flat plate flow over a flat plate, how to create the computational domain like in a y direction. You don't know the height. If you give a very long height, the number of equations are going to be more because number of grids are going to be more, the number of nodes are going to be more. Similarly, here also, if you take a very complicated geometry, then unnecessarily, but it comes with the experience only. And specific flow conditions and the properties, you have to select the flow conditions as the properties, select the models, like it's a laminar flow or a turbulent flow, or it's an incompressible flow or a compressible flow, it's a density driven server or a pressure driven solver. Then you have to specify initial and boundary condition. Okay. Now, once you geometry you are creating, that time how it will understand that how will you correlate with the basically whatever models or whatever initial or boundary condition you have selected. That is basically through the grid generation. So I told you there is a sponge analogy. Either you divide the computational domain in small segment, or you fill up the computational domain with a known figures, like in a three-dimensional object it's a tetrahedral figure, if it's a hexahedral, or if it is a two-dimensional, if it is a square or rectangle, in that way. Okay, and specific numerical parameters what you have to solve, and the solving the convert solution. Once you get that, you have to analyze the post processing, and then you have to see the uncertainty assessment, whatever you have solved, that is correct or not, that is realizable or not, that is physically making some sense or not. Okay, this is the CFD process. So whatever we have discussed, first geometry description, then we have to give this basically the next step will be grid generation, and then in a CFD software, and then after that you have to give the flow condition, more select the model, give the initial and boundary conditions, and specific numerical parameters, like you want to solve the pressure velocity in the simple. By default, the all the softwares will have some by default. When you are learning, first you use by default, but when you are doing some research or really doing some problems, then you have to see that what scheme is suitable for that. Otherwise, may not be getting the convergence very easily. Okay. So this is a typical approach. We take CAD or CAE integration, then we basically engineering drawings, and then we do AutoCAD. There is a IGIS format which can take the all the if you create a CAD drawing, then IGIS format will be able to take that format in any CFD software. There's an internationally validated format. So all the softwares, they provide the IGIS format. So if you get a CAD or CAE drawing, it will take in IGIS format, and you can incorporate that in Fluent. Now, flow conditions and all properties required are unique each flow code. I told you very easily that flow condition in a CFD software, there is a doubt. In a Fluent, you can't tell my Reynolds number will be varying from 100 to 1 million. Okay, that you can't do in Fluent because it's a generic software. CFD software requires all variables in dimensional form. But if you are a focused application, when you're writing your own code, then you basically vary Reynolds number 10 to 100 or 10 to 1000 or 10 to 1 lakh. So you have to calculate basically Reynolds number. What is that? If you are focusing your research from 10 to 1000, each of these values you have to calculate and give the parameter, physical parameters like velocity, etc., viscosity anyway with the velocity, etc., based on that, and that will give you the different Reynolds number. It's not a dimensional form in a CFD software. Okay, these doubts people have generally. So selection of the models like laminar or turbulent, and in turbulence also you are going to take a direct numerical simulation, or a Reynolds average Navier-Stokes equation, or a large GT simulation, or detached GT simulation. What model you will take, that will depends on your results also, different thing, and there are different models in turbulence also. So it's not in the scope of the work, but properly in a multi-phase, like you are going to take a volume of fluid model, or you are doing a mixing model, or you take a Eulerian Lagrangian model. So this model selection is one of the key story for getting a right results. Now, after you select the model for steady and unsteady flow, the initial, for steady flow, there is no time derivative, so you don't need an initial condition. But in a unsteady flow, you have to give an initial condition. For a steady flow, the boundary condition itself is going to suffice and solve the problem. like no slip at the wall, you know, from the fluid mechanics class. Then periodic boundary condition is one of the boundary condition where we use in heat exchangers, where repeating type of flow is occurring. The inlet velocity, the mass flow rate, the constant pressure for constant natural convection, outlet constant pressure or velocity, in turbulence buffer zone, zero gradient, non-reflecting, compressible flow, etc. So there are different boundary conditions are there, and you have to appropriately. I'll tell you one thing: in the same problem, if you just change the boundary condition, because you are not going to get a realistic result. You can try with a simple problem and then see that you are giving a pressure inlet or pressure outlet and specifying the mass flow rate also, it will not convert. So very important to know is that what type of boundary condition is applicable for my case. And these are generic software, so you have to go through their own manual, how they have implemented the boundary condition, and see that these are fitting with your application. The initial condition is the where in the time step t equal to 0, where the starts the flow, that is required. And initial condition, I will tell you. Okay. Initial condition, I will tell you that at t equal to 0, it will ask you that what value you have to give. Okay. But this entire Navier-Stokes equation is going to be solved for t equal to 0 to t equal to say 1 minute or 2 minute or 5 minutes, whatever you have to see. So you have to take, you see that there is a del u del t term. Once you basically discretize it, that will create the ui plus 1 minus ui divided by delta t. Okay. So this delta t is the time step. This time step you have to give. So we are assuming at t equal to 0 to t equal to 0.1 second, there is no change in the whatever change will happen at 0.1 second only. So we are assuming that and taking 0.1 as a 0.1, 0.01, 0.001, whatever time step you want to study, that has to be properly selected. And I'll give you a caution that per time step, don't allow more than 20 iteration, 20 to 25 iteration. Like if you want to take say 5 minute and 0.1 is your 0.1 second is the time step, then you have to do for the time the 5 minute into 5 into 60, 300 second divided by 0.1. So 3000 say time step will be there. Okay. Now this 3000 time the Navier-Stokes equation is going to get solved for how many number of millions of grids you have given. So don't stress your, if you are not getting within 20 iteration and taking a reasonable delta t 0.1 or 0.01 or 0.001, then don't go beyond that. Now, grid generation is one of the key structure or the key point of this CFD process. That is, once I told you I am filling up this entire geometry with a known structure, triangular structure, or I have in a radial this kind of structure. Okay. So in a schemes like finite difference that give you a structure, these are the unstructured grid. Okay, these are the unstructured grid. And application like thin boundary layers best resolved in highly stretched structured grids like these kind of things. And unstructured grids are usually used for complex geometry. Otherwise, you can't even go about it. Okay. Now, if I give you this example, that if I take these points as your nodes, cell-centered nodes, then if you have divided that in 20 by 20 or 100 by 100, whatever, then 100 by 100 number of equations you have to solve. So this Navier-Stokes equation has to be transformed in 100 by 100 algebraic equation, and that has to be solved also in a different time step, because you want to see that from 0 to 5 minutes. Okay, so grid is very important. Like if you are not making, like if you are making infinite grid, then you will get a very ideal solution, or the very close to analytical solution if you want to see. But there should be a optimization, like how many number of grids. This is called grid independent solution. After that, the solution is not going to change appreciably. Okay, so that we called as a grid independent solution. I'll tell you this one. Like this is a converge solution. Okay. So number of grids you have enhanced. Don't give any number of grids at the first point. You first do 10 by 10, 100 by 100, and then 200 by 200, and then give the millions of grids. Because you have some problems in the model or boundary condition implementation, don't take the risk. It will hang, or it will run for, if you have a sufficient computational power, it will run for 7-10 days, and you are not going to get any significant result out of it. Okay. Sometimes what happens is, it's not true for CFD software, because it takes it in a unstructured grid in a sponge analogy. But if you want to write your own code, say, so you are familiar with this kind of grid, and your physical domain is such irregular. So what you do is, you do a mapping. This is called grid transformation. So you do a mapping from physical domain to the computational domain in a eta xi coordinate, and then is called body fitted grids, and then you transform that, because your result should be, the contour should be placed on the physical domain. So you have to do an inverse transformation. You understand what I'm trying to say? That physical domain actually is irregular, highly carved, etc. Say impeller of a pump. But your Navier-Stokes equation can solve only in a Cartesian axis. So what you do is, you transform the grid in a computational domain, which is the two-dimensional plane. So, and this, there are several ways to do that. You will learn in course of time. So physical domain, but you have to invert that, because physical domain, if you tell pressure here something like that, or velocity here something like that, that doesn't mean, because that doesn't physically exist. You have to invert that result also. There is a transformation and inverse transformation. Okay, this is called grid transformation. Now, due to there are some numerical parameters which actually gives you some kind of problem. There is a factor called under relaxation factor. Okay, and you will learn when you will learn the tridiagonal matrix, or what pentadiagonal solver, etc. This under relaxation factor basically has no, the turbulence problem for pipe, you can say it's 0.3 for continuity. So that kind of things exist, but no generic as such rule is there. These are all comes with the experience. Under relaxation factor, what it does is, it's basically foster the convergence speed. Foster means that speed up the convergence speed. Otherwise, if you don't give the right kind of under relaxation factor, the best thing is first you try the default one. If it is not convergence, then you should make a doubt about your boundary conditions, etc. if you are sure that you have implemented the boundary conditions is correct and implemented it correctly, then you doubt about your under relaxation factor. Then your under relaxation factor basically will be selected, and there is a domain specific range are available in literature for under relaxation factor. Okay. Now, if you keep on iterating, you have to give, this is the convert solution. You have decided that, okay, it will transform 1 to, I have decided 10 to the power minus 6 or something like that, whatever residuals I have, and this will be asymptotically parallel to the iterations axis, and this will be the solution converged. Okay, you will get a pop-up message from the software, the solution is converged. Now I get a convert solution. So whatever we have started, that we have started with U, V, W, P, T, etc. But what I am going to do, I will get a numerical value. I have to physically see that what is happening, the flow, how the creating a vortices, or what is the shear stress, what is the forces, what is the moments, how the flow is happening. So we have to visualize it, and this post processing part is visualization. Okay, post processing part is visualization. So in a you can plot your velocity with time. This is a basically XY plot. You can plot a contour, basically that is a velocity contour, pressure contour, temperature contour, etc. 3D carpet plots are also possible. These are all inbuilt feature of a CFD software. If you are not interested in that, or you are writing your own code, there are softwares like TechPlot or MATLAB, they can do that. Okay, vector plots or streamlines plots, the animation, how it's behaving with the time, how your droplets are generating with the time. Okay, this is, I will give you an example. Post processing of a parallel plate flow, there is a two parallel plates. Okay, I have a velocity field I have plotted here, right? I have solved it correctly. I know that everything is correct. This is my color range 0 to 0.25, right? I am getting a maximum velocity here. You can see this is a maximum one, maximum velocity at the center near about the core, and minimum velocity at the wall. This is a cross check that your no sleep has been properly implemented. These are the two plates, right? So you are getting the zero velocities. Just see the zero at the wall. This is the entrance of the flow, and at the wall you are getting a no sleep. So you are getting a blue color, the deep blue color here. So this is the no sleep has been properly implemented, and that's the way you should basically visualize the results. Okay. Okay.
Yes, sir.
Now you get the results. You can give the pressure contours of some different velocities in different gadgets, etc. So those things are there. Now another plots you may not be familiar with, that is called vector plots, which is basically half of, this is a two-dimensional plane. This is basically half of root over u square plus v square, where u is the x directional velocity, v is the y directional velocity. Okay, so this is a vector plot. This is a typical lead driven cavity example, where there is a cavity and there is a lead over it, and you are giving a velocity in the lead, so there will be a circulation inside the cavity. Okay, so you are getting a basically flow like this, circulation inside that, and these are called vector plots. These are the streamlines, pressure contours, etc. has been plotted. So you have to do a post processing to understand what is happening inside the flow, and then understand the flow physics. Now, whatever results you have generated, that has to be properly assessed. That means there are two terms. One is verification, one is validation. Verification is I am taking, say, I am talking about, first, let's talk about the finite difference. I am taking a 100 nodes, okay, and I am taking a first order approximation or second order approximation, and I am solving that with the Taylor series expansion. You can easily know a second order approximation means after onwards that term you are dropping. Basically, you are neglecting those terms, higher order terms. So there will be a truncation error. Okay. So, so that truncation error, that will give you the right kind of solution or not. That you have to watch term. You have to, those things are called verification. So your code has to be verified. Depends on those iteration aspects, those truncation error, etc. And validation is basically, say, I'll tell you one example. This cavity problem, I'll take that in space and do that. What will happen? What will happen is that basically the gravity is not going to be there, right? So if you take this test here and find that it's working fine, then you can put G equal to 0 or something like that. And then you will get a different pattern for the flow. So these kind of benchmarking or validation is required, because it's not necessarily the always you will get the experimental data. So if you establish your flow or certify your flow, your code is certifying in the on the ground, you can extend that on the space also where there is a negligible gravity. So those things are called benchmarking, or you can do, because experimental data may not be available for all the experiments. Okay. So I know you may get a inlet and outlet data, but you may not get the each and every point. That kind of experimentation takes a long precision experimentation techniques to do that. Okay. Without PIV, you will not be able to see the flow like that way. PIV means particle imaging velocimetry. Now, certification, etc. Yeah, I'll just go by benchmarking. Like if you develop a code, or if you know that you have done that problem correctly, so you see this others result, that whatever they are predicting, so that is called benchmarking of the problem. Or if you are developing your own code and try to sell that or try to use for some others problem, then you have to benchmark. There are 8 specified ASME problem for that. So all the codes has to pass through that bench 7 or 8 problems that able to satisfy the in that accuracy or not. Okay. Otherwise, experiment validation is already there. If you want to analytically validate, for example, pipe flow, developing pipe flow, etc. So analytical validation is also possible. So verification is basically you are doing the process correctly or not, your iteration schemes, your truncation errors, these are in reasonable manner or not, and validation is basically with the experimental results or analytical validation or some others benchmark result validation, numerical result itself. So that is there. Okay. I have some suggested reading. The H.K. Versteeg, An Introduction of Computational Fluid Dynamics, Fraser and Perick, Verification and Evaluation of Computational Science, or F.M. White, The Viscous Flow. Another book I should suggest, if this book, if you study, you will be able to use any CFD software, which is written in finite volume method only. You will be able to use this in CFD software. So one book I'll suggest, I not listed, because these days people are not trying to write code. So if you want to really develop a new code, understand the schemes inside, then you should use a numerical heat transfer and fluid flow written by a very famous Indian scientist located in Minnesota, S.V. Patangar. Okay, very famous book, only thin book. You can complete that in overnight, but go over it different times. Then only you'll be able to get the juice of it. Okay.
Hello.
Now I'll be happy to if there is any question.
Yes, I we invite participants. Please ask their queries. Either they unmute your mic or can write in the chat box also.
Dr. Sharma, please take
Any participant? Hello.
Dr. Sharma, please.
Yes.
Please take some query from the chat box.
Yeah. You write your queries in the chat box. Any one of you? Sir, one query is from Vaibhav Mishra is there.
Open form.
Hello.
Yeah.
Am I audible,
I have
sir?
seen
Yes.
ANSYS or open form.
Yeah.
It's open form.
Yes, sir.
Stability analysis will be better in open form.
Another one is from Ramakrishna.
Okay, Ramakrishna, I explained that very clearly, but I am repeating that again also. Say, well, if you pose a problem, then you basically not getting a convergence. You have taken a geometry, you properly impose the flow physics, give the boundary condition correctly, and you are sure about that. Then you should doubt about under relaxation factor. The first doubt, if you are not getting a convergence, means your grid and boundary condition. First is not the under relaxation factor. If you impose that two things correctly, then you should think about under relaxation factor. Yes, open channel flow.
Other queries.
Open channel flow. In the open channel flow, you can see in CFD software.
Another one, Ayush Pandey.
Numerical heat transfer and fluid flow. Numerical heat transfer and fluid flow by S.V. Patangar, Hemisphere publication.
So one query was also there previously. The name of software used in CFDs. Somebody asked, sir.
Okay, there are ANSYS Fluent, there is CFX, they are all in ANSYS suite now. CFX Fluent, and then you can have Star CD, then you can have Console. You know, this everybody means if you want to use a first CFD software, not knowing much about the CFD, I will suggest that you use ANSYS suite, where you will basically you will have CFX and Fluent together, and you can compare that too. If you are, or Star CD, if you are a little confident, and then you use OpenFOAM, or you use because OpenFOAM, all the models are very not well. Some models are proprietary models, like Presto. One scheme is there in term. So that is a proprietary model that may not be available in OpenFOAM. Okay, so that is there. And then console is also very good because you can give the boundary your own equation and get the solution. Here also you can modify the equation in a CFD software through source term, etc. Because other terms doesn't change that much. Only the source terms gets changed.
From Ramkrishna also. How to select different models such as K epsilon, K omega, etc. for doing
These are all
simulation.
turbulence model. I don't have the scope to go to the in details of this. There are some relative advantage. The one equation model, two equation model, K epsilon model, K omega model, etc. So I was about to tell Professor Tiwari that there should be a turbulence modeling class
Yeah,
in this.
there is a separate session for the turbulent modeling.
Okay.
So, Dr. Sharma, please close.
Anyone? Yes. Okay. Thank you, sir. Thank you so much, sir, for such a nice, wonderful talk. You discussed why CFD and where it is used in different engineering sectors. Not only in the engineering sector, it also used in sports like aerospace, appliances, hydraulics, power generation, etc. CFD has now many applications. Typically, you focus very well on the CFD code, typically designed as per the problem. CFD processes like geometric description, flow. You discuss the mathematics of CFD in a very easy way. So thank you so much again. Thank you so much. We are grateful to be found here in this talk. And now I would like to invite Professor Shailin Sinhaji, Department of Mechanical Engineering, IIT Lucknow, to please join us and give. Hello. Hello.
Hello. Yes, sir.
Shailin
Thank you,
sir.
Ajay, and thank you, Arun. Am I audible?
Yeah, sir.
Okay. So,
Thank
thank you again, Ajay and
Yes.
Arun. And good afternoon to all of you. I am Dr. Shalin Sinha, professor at IIT Lucknow.
Good afternoon.
Now, it's my pleasure to propose vote of thanks for this event on behalf of the Institute of Engineering and Technology, Lucknow, Department of Mechanical Engineering, and myself. I express my sincere thanks and gratitude to Dr. Pradyumna Ghosh for sparing his valuable time to with us on the occasion of this faculty development program on the advanced computational fluid dynamics. Dr. Ghosh is a professor at IIT BHU and well known to all of the participants. He is the not only in the field of the computational fluid dynamics, but he distinguished himself in the field of education as well as technical and scientific research in the country. CFD is a very complex field, and as the topic that is your advanced CFD, it really is a very complex topic. But Professor Ghosh has explained the topic in such a nice, simple, and interesting manner that we are all encouraged about it. I thanks Professor Ghosh for excellent coverage of the topic. I am sure that the knowledge we gain from this lecture will definitely help us in our studies and future, and especially transferring knowledge to the students. We are all the faculty members, and it will be very useful for us to transfer this knowledge to our students also. Once again, I would like to thank Professor Ghosh for taking out time from his busy schedule and enlightening us with the knowledge. Thank you, Professor Ghosh. Thank you all. Thank you so much.
Thank you.
Thank you so much.
So the next session is at 3:15. The next session is at 3:15. Dr. Barun from IIT.
3:15. Yeah. So
Yeah.
all participants